All right, welcome again to our statistics lesson. We just finished a chapter dealing with confidence intervals. Confidence intervals are just one of two different ways that we have to do statistical inference. Now, when we do a confidence interval, we start with our estimation based off of a sample, and we're trying to figure out what our population parameter would be off of that. So it starts with the sample and tries to guesstimate where the parameter actually would be. The other way to do that, which is a significance or a hypothesis test, is to kind of start the opposite way. You start with what you think the population is sitting at. You think this is what I think their parameter is going to be, and then based off of what your sample says, you simply say, does it make sense? So a significance test, and I actually think that word is quite appropriate because it's saying, is my evidence significant or not? It's also our hypothesis test, because we're testing a hypothesis, tests the validity of a claim. In other words, I think this person is guilty of a crime, and a hypothesis test tests that. We are trying to evaluate the truth of a claim. Now, right now, the claim that we're going to be measuring, the claim that we're going to be judging, is going to be the population proportion. Now, you can also do it on the mean, and we're just going to take it one step at a time. Now, everything that we do with a significance test is trying to determine if the hypothesis, if what we're being told is actually true, what's the likelihood of my results occurring in real life? And so that is our probability that we use to measure the data and to either agree or disagree with the claim. So we're going to be talking about the logic of these tests, how to perform them, and again, we're just focusing here today on population proportions, P's, and then looking even closer at that relationship between confidence intervals and a hypothesis test. Again, a confidence interval starts with the sample and uses that to estimate the parameter. A hypothesis test starts what we think the parameter is and uses a sample statistic to either justify or contradict that claim. Now, take this claim, for example. Some basketball player claims he has an 80% free throw shot record. That means that he thinks that out of all the shots he takes, he should have 80% accuracy. 80% of them should go in. Well, we don't know if we believe him or not, so we're going to test his claim. He is going to make 53 throws. Okay, now in those 53 free throws, he only makes 32 of them. So that means his proportion, his actual free throw for those shots is 32 out of 50, or 0.64. Now that's a 64% free throw rating. Okay, so what we're going to do is we could use software to simulate. All right, now if this guy did have an 80% free throw, what would that result in? So just like we used the simulator before, here we've got it pre-done, saying, okay, if he really did have an 80% free throw rating, we're going to take 400 different sets of 50 shots. So each sample contains 50 free throws of a person with an 80% accuracy rating. And if that is the case, what is the distribution of his resulting free throws? And you can see here, it's an approximately normal curve because we have quite a few shots. And if we look at this sample run of data, there were only 3 sets where he made 64% of his shots or fewer. Now we can use this data of simulated free throws to actually determine how strong his claim is about whether we believe that based off of this one sample that we can maybe contradict his claim and say he's a liar, liar, pants on fire. So the observed statistic is not very likely. You see where it falls here? Only 3 out of 400 different times did his free throw rating get that low. Then that tells me that if the true value of his parameter, his true free throw average, is 80%, yeah, this is not going to happen very often. To me, that's pretty convincing evidence. And that's what a hypothesis test is all about. Saying, okay, based on the evidence, we might conclude that the player's claim is incorrect, because in reality, there are only 2 possible explanations for why he would have only made 64% of his free throws if his true proportion is 80%. Okay, so, well, what could happen is he's actually telling the truth, but he was just having a really, really bad day, very bad luck, and something that we didn't expect to happen actually did. Or the population proportion is actually less than 80%. His free throw rating is really not the 80% that he claims, which is why the sample result is not unlikely. So what we have to do is we have to decide whether or not the outcome is likely to happen, and is that, if that claim is actually true, whether the evidence that I have is strong enough to support that the claim is not true. So again, what we're saying is an outcome that would rarely occur, such as this case, a free thrower with an 80% free throw rating only making 64% or 62% of his free throws, is that one piece of evidence strong enough to say that he is lying? And that's the whole purpose of a hypothesis test. Now, confidence interval lets us estimate a population parameter from a sample. Okay, remember again, we start with a sample and we try to estimate where the true parameter is. In a hypothesis test, we start with a claim about the population. And then what we do is we look at the results of a sample. Does the sample itself support or contradict our claim? So we were looking before at a basketball player who said he had an average of 80% free throw completions. So what we have here, and this is extremely important notation, this 80% is our null hypothesis, and we denote it here with an H sub 0. That assumes that the claim is true. Our null hypothesis always assumes that the claim is true, or the idea that nothing has changed from the previous claim, because sometimes they'll say in the past the true proportion was 80%. Well, we're going to say that nothing has changed from that. So the null hypothesis is written as H sub 0 or H sub O colon P equals 0.8. My null hypothesis is that the probability of his shots on average is 0.8. The alternative hypothesis, in other words, we're saying, okay, if this is not true or something has changed, what would it actually be? Well, we have to be very careful here because we don't have that much data. All we know is that something has changed or this is not true. So the alternative hypothesis is that the probability is not 0.8. Now sometimes we won't care about it being just exactly not this. Like if he claimed he had an 80% free throw rating, would we really care if it was better than that? And so a lot of times we would say, okay, what would only bother me? And that would be if it was less than 80%. So P is less than. So what we have from all of this is you always start with your null hypothesis such that the parameter equals the value that you have. The true population proportion or true population mean is the value that was claimed. That's always going to be your null hypothesis, always and forever. P equals what they give you. The mean equals what they give you. That's your null hypothesis. Your alternative hypothesis, H sub A, is whatever would bother you the most. Sometimes it is a one-sided or one-tailed test, saying, you know what, whatever their claim is, I'm not saying that the parameter is just not equal to, but only worries me when it's less than, or when the truth is that it's actually greater than. It's called two-sided or two-tailed when the parameter is not equal to the value. Now, the only way that we can figure out what the true alternative hypothesis should be is if we read the problem carefully. Sometimes it will just be whether or not we believe that the null hypothesis was true. And the null hypothesis is true whenever this holds, and it's not true when we're not equal to. But in real life, a lot of times, okay. So, probably the best explanation for this is if we're looking at a jury trial. And I'm going to talk about this over and over and over again throughout the course of the class, because to me, this is something that you've dealt with and you've seen. Ever since you were little, you knew about what a trial was and when a jury can find somebody as guilty or not guilty. You've also heard the saying that everybody is innocent until proven guilty. And that's what our hypothesis test is worked on. We assume a hypothesis test is true until we can prove otherwise. Now what that says is that we retain the null hypothesis, we keep it until the facts that are presented show us beyond a reasonable doubt that the original hypothesis is not true. And it's that idea of a reasonable doubt that centers around this hypothesis test. Then and only then, when we have enough reasonable doubt, can we reject the null hypothesis, in this case of innocence, and declare the person guilty. The same logic is going to hold true for all of our significance tests or our hypothesis tests. What we do is we begin by assuming the hypothesis is true. So tying that back to the jury, we begin by assuming that the defendant is not guilty. Then what we have to do is consider whether or not the evidence or the data at hand is consistent with that true claim. So whether or not the evidence that the prosecution presents is consistent with the person being innocent or not. If they are, if the evidence that we have is consistent with my null hypothesis, all we can do is retain the null. All we can do is retain that idea of not guilty. So if they are not, then we have to ask whether they are unlikely beyond a reasonable doubt. What that means is if my evidence does not support my initial claim, we have to know, is the evidence strong enough to say beyond a reasonable doubt that the null hypothesis, the initial claim, was true. So what happens if the defendant is innocent? Okay, so if the evidence is not strong enough to reject the presumption of innocence, in other words, I'm in court, the prosecution's evidence is just not strong enough to get me beyond that reasonable doubt, then the jury comes back with a not guilty verdict. Notice this is hugely important. They do not tell you that the defendant is innocent. They're basically just telling you that there is not enough evidence to convict. There's not enough evidence to say beyond a reasonable doubt we get to reject their innocence. The defendant could be innocent. The defendant could be guilty. Doesn't matter. We have no way to be sure. We have doubt. So when we put those into statistics terms, we say that we are failing to reject the null hypothesis. So we are never actually saying that the null hypothesis is true. We're never saying the defendant is innocent because we don't know if that's true or not. We are simply saying that I don't have enough information to say the opposite. So in other words, sometimes we say that the null hypothesis has been retained. We're not going to use those words. We're just usually going to say that we failed to reject. For example, in the case of the jury, they failed to reject that the defendant is actually innocent. So in trial, the burden of proof is on the prosecution. It's the prosecution's job to get that reasonable doubt, to get enough evidence so that the jury believes beyond a reasonable doubt that the defendant is not innocent. The hypothesis test, the burden of proof is on the unusual claim. And basically what that's saying is my one sample, is my one piece of evidence strong enough to show beyond a reasonable doubt that the null hypothesis was false? Now, here's the cool thing. What is that point? Where would your reasonable doubt come into play? Well, statistics, this is so much better than a jury because we actually get to set that balancing point when somebody goes from innocent to not innocent, from guilty to not guilty. And that level of significance is always denoted by a little alpha. So when we have evidence that supports the null hypothesis, we say we failed to reject the null. Okay? It does say in here accept or retain the null, but please, 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 just for safety's sake, because sometimes these words do not necessarily hold true, just say that if your evidence supports the null hypothesis, for example, if my free thrower claimed he had an 80% free throw rating and my sample said he has a 78% free throw rating, that's not strong enough evidence to show that he is lying, so I failed to reject his 80% claim. If the evidence in the sample shows that my null hypothesis is false, for example, when I said, hey, wait a minute, look at how rare it is to occur to have a 80% free throw rating and then only make 64% of it, then that tells me that I reject the null. This is because the hypothesis test is really a sliding scale. Whatever you want to talk about here, here's my scale. And we have certain points along my scale where we get to reject the null hypothesis or fail to reject. Okay? Think about it this way. If we're talking about the defendant, here's where he's guilty, here's where he's innocent. This is where the defendant has committed every single crime or atrocity or whatever you want to say that the prosecution claims. Absolutely every piece of the story is true. Now the other side of that is that absolutely every piece of it is not true. Maybe, for example, the defendant wasn't even in the country when the crime occurred, or the defendant had never known the victim, or the defendant had no clue or had no ties to it whatsoever. There's a huge sliding scale here. 100% guilty, 100% innocent. Well, we have to somewhere set this alpha to where I get to claim that the person is, in fact, guilty. And we set that all the way over here because we want to be beyond a reasonable doubt. If the person is right in here when it comes to their guilt or innocence, that's not strong enough necessarily for me to want to, I don't know, give them the death penalty or lock them away for life. It's very important that we make sure we know where on the spectrum we fall. So in reference to what we're doing, the level of significance is a measure of how certain we want to be. How much doubt are you willing to accept? Now, how much doubt we're willing to accept really is dependent upon what the situation is. But all of this goes back to the area under the curve, z-scores, your normal probability. So we're going to be using a lot of the normal distribution model still to figure out what that probability is. What we're going to be looking at is the probability that something occurs if the null hypothesis was true. So we're going to use the model proposed by that null hypothesis to calculate the probability the event of what we've seen could actually happen. That's called our p-value. The probability that my sample actually really does occur, assuming my null hypothesis is true, that is my p-value. It is the probability that my sample can occur given the null hypothesis is true. The smaller the p-value, the stronger the evidence against the null hypothesis provided by the data. So that means the smaller your probability is, the smaller the probability that a basketball shooter would actually get 64% of his shots If his true overall rating was an 80%, the smaller that probability is, the stronger evidence you have that your null hypothesis, the original claim, is not true. When your data is consistent with the model from the null hypothesis, like we're saying the basketball player really does have the 80% free throw, and my data, like let's say he had that 78% that supports it, that would say the probability of that occurring, that probability is probably very high that he would actually have a 78% in maybe one game or so. So that is not enough for us to reject the null hypothesis. So we would say that we fail to reject the null hypothesis. Here it says retain, but you want to be careful. I want to scratch that out. I don't want to say retain. I want you to say fail to reject. Because I have seen some very picky people who say that retain is too strong of a word. Now technically it's okay, but let's kind of get in the habit of saying something that will not get us into trouble ever. If my p-value, for example, the probability that a free thrower actually has a 78% shot is, let's say, 42%. That's a pretty strong probability. So that's not enough for me to reject, so I fail to reject the null hypothesis. You can never, ever, ever say that we've proven the null hypothesis. You cannot say the null hypothesis is true. All you can say is we fail to reject. Because P says what is the probability that the sample would occur due to natural sampling variability. Okay, we talked about that before. We said due to the fact that my samples are going to vary, if I don't pick the same shots every single time, each sample is going to have a different outcome. Well, the p-value says that that is so, the probability of getting that is so small that it doesn't work anymore, or that the p-value is so big that we fail to reject. Large p-values fail to give convincing evidence against the null. It's not enough evidence to say that the initial claim was false, because it's saying what we saw is likely to occur just by chance. It's not unreasonable to assume that that would occur just by chance. If the p-value is low enough, we reject the null hypothesis. If it's not low enough, we fail to reject. We reject because the probability of something like that occurring is not very strong at all. In fact, it's rare. Small p-values are evidence against your null, against your initial claim, because it says that that result is unlikely to occur if the original hypothesis was true. So, when we're trying to make our decision, exactly how small is small enough for my p-value to actually reject the null, to believe that somebody is lying, or to believe that my initial claim is not true? Well, it really is context dependent. I mean, frankly, whether or not I'm going to believe that taking, I don't know, emergency is going to help me shorten the length of my common cold, I don't need too much evidence in order for me to actually go with it. But if I'm going to be sentencing somebody to the death penalty, I need very strong evidence because of the consequences. So when we're screening for a really bad disease, and you want to be sure that we get to treat those people who are sick, we really might be able to reject the null if I have a fairly big p-value, say 0.10 or 10%. But on the other hand, what happens if the side effects of that are bad? A long-standing hypothesis, a long-standing belief held by many to be true, usually needs stronger evidence or a corresponding stronger p-value, because our p-value is that evidence, to reject it. Another factor in the p-value is the importance of the issue. Okay, so we're looking at how old is the long-standing belief. How important is the issue? So what we go off of in general is a p-value of 0.05. That's our alpha. Our alpha is typically 0.05. Sometimes researchers will use a stricter cutoff of 0.01, or more general, more generous, more liberal of 0.10. So our typical go-to is 0.05. That's our typical alpha level. But sometimes we can be a lot more stringent and say 0.01. Sometimes we can be more generous and say 0.10. It all depends upon the situation. But no matter what, a small p-value is evidence against your null. A large p-value means there's not that much evidence against. What you have to understand is that little or no evidence against the null is not the same thing as being a lot of evidence for the null. Remember in the case of our jury, we are not trying to determine whether or not the person is innocent. We're trying to determine whether or not the person is not guilty. Okay? So we're saying again, no evidence or little evidence against the null is not the same as saying a lot of evidence for the null. Your conclusion should be accompanied by the value of your p-value. So whenever you say, okay, either I reject the null or I fail to reject the null, you must always include your actual p-value and your alpha level. If possible, go back and include the confidence interval. Because what you're saying is, I don't agree with what my initial claim says. The confidence interval then turns around and says, I believe where the truth lies is within this range. Don't just declare the null hypothesis as rejected or not rejected. What you're going to do is you're going to say, with a p-value of, which is less than alpha, then we say we reject the null hypothesis. Or with a p-value of, which is greater than alpha, we fail to reject the null hypothesis. What that allows us to do is that says that, okay, if somebody is reading my research and doesn't quite agree with where my cutoff data was, where my cutoff point was, they can then make their own decision and say, okay, you might reject the null or you might fail to reject, but with my level of certainty that I need, maybe they don't quite agree with you. There are 4 basic parts to a hypothesis test, 4 things that anybody, whether that's your employer, somebody who's evaluating your research, or an AP test grader, is going to look for in order to say that you've covered all of your bases. Now in a hypothesis test, sometimes what we'll do is we'll break our work up into 4 pieces. With the hypothesis itself, that includes the null hypothesis and the alternative hypothesis, plus any conditions that you, actually no, the conditions would fall under the test, so you've got any conditions that you have to meet, and then you describe what test you're actually going to perform. Is it a one-tailed test? Is it a two-tailed test? And then we will have different types of tests later on. The mechanics, which is your work shown, you actually go through the process, and then the conclusion. And remember, your conclusion must always be in context. And your conclusion would be based off of, with a p-value of whatever, being less than or greater than alpha, we fail to reject or reject the null hypothesis that, and then you go into all the basics. So what are all the requirements for each of those steps? The hypothesis must be your null hypothesis, where you state H sub 0, H sub O, colon, the parameter is the hypothesized value. You can either write that out in words or you can write that out in symbols. We're saying P is equal to whatnot. Your alternative hypothesis, your H sub A, says, okay, what do you need to reject the null hypothesis, or what would our alternative be? You do need to specify how many tails that would be. Is that upper tail, lower tail, or two-tailed, greater than, less than, or not equal to? You must use correct notation. The test itself, again, we are going to have a lot to choose from, but right now we don't. So right now we're going to be using a normal curve or a z-test. You're going to state and check your assumptions. And your model step should always end with a statement which says, because the conditions are satisfied or met, we can model the sampling distribution of the proportion with a normal model. Okay? Watch out. It might say that your conditions are not met, so we can't proceed. And if that's the case, you do get to stop and reconsider. The mechanics is basically show your work. And remember, statistics is almost more about the work that you show and the justifications that you make in the final conclusion. So you can report your test statistic, and when we're talking about a normal model, our test statistic is the z-score. The p-value, that's the probability of something occurring given simple random variability, because your ultimate goal is to get that p-value. The p-value is the probability that the observed statistic could occur if the null value were correct. And the very last thing that we do is we state our conclusion. State the decision. Remember, we reject or fail to reject. Please make sure that you're using these terminologies. Include a linkage to p. You must always, always include that. Say, because the p-value is whatever it is, which is either greater or less than alpha, we fail to reject or reject the null, and always put it into context. Every single chapter that we're going to see coming up is going to use this same four-step procedure. So for now, what I'm going to be looking for every time that you do this is to say, did you state the hypotheses, both null and alternative? Did you check the conditions and name your test? When you do that, you always want to specify whether it's a 1 proportion or 2. Again, we're going to talk about that a little bit later on, and whether or not you follow the normal model. You're going to need to, this is your work here, so this is hypothesis, this is test, and then this down here is your work shown. You have to find the standard deviation and the z-score that goes with the values that you have, and use the z-score to find the p-value. And the last thing that you do, your conclusion, is compare the p-value to the level of significance to decide whether you're going to reject the null or fail to reject. So again, you need to make sure that we state the hypothesis, null and alternative. Check your conditions and name your test. Find the standard deviation, the z-score, and then use the z-score to find the p-value. This is all kind of all wrapped up in one little awesome button that I will show you later on. And then you're going to compare your p-value to your alpha to decide whether or not you reject or fail to reject the null. And that's pretty much it for today. So it's extremely important to me that you either remember the four-square approach and what goes into each of the squares, or you remember this five-step procedure. Did you state your hypotheses, check your conditions and name your test? Did you show all your work to find the standard deviation and z-score, and then use the z-score to find the appropriate p-value? And then in your conclusion, did you tie your p-value to your alpha to make the decision whether or not you reject or null or fail to reject the null? Okay? So make sure you understand either your four steps, hypothesis, test, mechanics, and conclusion, or the more specific broken down approach. State the hypothesis, conditions and test, show all of your work finding the standard deviation, z-score, and p-value. Compare the p-value to the alpha and decide whether or not you reject or fail to reject the null. Make sure that you can do that, guys. See you in class.